Okay, so welcome to chapter 9, frequency analysis. So I'm Dr. Nur ELIZA. Okay, so basically for this chapter, we have two parts, which is introduction to probability distribution function, and this is actually a part of frequency analysis. And part 2, the method used to conduct this frequency analysis. So here for our syllabus, there are empirical frequency distribution, normal probability distribution, and extreme value theory. Okay, so there are several important terms and components which you need to understand first. So it is probability, random variables, sampling, summary statistics, and also graphical displays. So the first term is probability. So what is probability? It is actually a measure of how likely an event will occur. Okay, or a number expressing the ratio of favorable outcome to all possible outcomes. Okay, so probability is usually represented as P, okay, big P. So what is it? For example, this is some of the famous example that we usually use is, for example, if you play a cards, okay, and then you want to take out one card, so there is, you can calculate the probability of what card will appear. Okay, and the other one is when you roll a dice, dadu, kita baling dadu. So what is the probability of what number to appear? So okay, so that is examples of probability. Okay, so we know probability. What about variable? I mean random variables. So random variable is the data. Okay, it's a quantity used to represent some probabilistic uncertainty. Okay, so for example, we say X rainfall. We may use the symbol as X. So rainfall is a random variable. Okay, and it can be described by a probability distribution. Okay, so what is probability distribution? So it's a set of probabilities associated to a values. Okay, so these values, we can say it as a values, data, or random variable. So in hydrology, uh, we usually use for random variable is rainfall, okay, or stream flow. So these two are random variables, okay, because we cannot actually calculate it. I mean, it's a little difficult to predict, so we may use statistics, okay, in this case, probability. So in probability, we have sample, okay, and we have population. So for example, this rectangular is population, okay, so we have, let's say we have sample set A, we have sample set B, okay, so both of these are actually in a population. Okay, this rectangle is a population. So in probability, we calculate using samples. Okay, so now sampling, which is sample. Okay, so what is sample? So remember the previous slides. Sample is the observation that we took. For example, here x1 until xn, the number of observation is n. So that is sample, okay, and then it comes from a hypothetical infinite population. So the previous slide shows you a rectangle. So let's say all the data is in the rectangle, but what we have is only the sample, which is sample A and sample B. Okay, and then sample space, set of possible samples that can be drawn from a population. So the space is the sets, the circle, set A, set B. So that is sample space. Okay, and then event, subset of a sample space. So in hydrology, we may relate it like this way. Let's say you have a data, rainfall annual maximum series data. So annual maximum series means each year you take the highest rainfall value. Let's say you have a 1 day rainfall. Every day in a year you have a amount of rainfall. So what is the highest each year? So when you get the highest rainfall each year, so that we call it as rainfall annual maximum series. Okay, so the population, it means all the data that exists, let's say from year 0 until a year infinity year, we don't know until when, so that is population. Okay, sample space is the annual maximum series. So that is the sample space. We take the annual maximum series from some sample space. So from set A, set B, okay, and then the sample. So the sample that we took is, for example, from 1990 until 2000. Okay, so that we have only 10 years of data. So that is sample. An event is, for example, we may say a 1-day rainfall or a 2-day rainfall. Okay, and because this is rainfall period, so events, it may depend on the rainfall period. So whatever data you have, the most important thing is it can be described in this way. Okay, the sampling, okay, it can be described according to these components, population, sample space, okay, and then the information on the sample and the event. Okay, another important thing is summary statistics. Okay, you should be familiar with this kind of statistics. It is also called descriptive statistics. For example, mean or average. Okay. Okay, in statistic, sample and population, in this case continuous data, it may have different symbol. Okay, so that is why there is this symbol for continuous data. Okay. So mean, variance, standard deviation, okay, coefficient of variation. Again, also in hydrology or probability, we have median, skewness. You may understand this later. So all the data that we have, we can actually display it in terms of graphical. For example, here we may plot it as time series plots, okay, as a histogram of frequency distribution, as a probability density function. We call this as PDF, okay, and CDF. CDF is cumulative distribution functions. And also, this is just an example. For example, we have flow duration curve. So this is kind of graphical displays. So time series plot is just a plot of the data. Here we have on y-axis is the annual maximum flow, okay, or discharge. And because it's annual maximum, so it means each year you will have one value, which is the annual maximum, which is the maximum flow in each year. So the x-axis is the year, the time. Okay, that is why it is called time series plot. Okay, so we look at histogram. Before it's on time series, but histogram is, it looks into the number of occurrence. For example, here the first bar is it is actually the data is between 25 to 75, right? Okay, so how many times this flow, okay, the flow between this range occurs, how many times it occurs? So let's say here is 88. So we plot y-axis is number of occurrence for the maximum flow in the range of 25 to 75, okay, and for the range of 75 to 125 here. So it is observed that it occurs 15 times. Okay, so this is what we call histogram. Okay, uh, it can be number of occurrence. Okay, and it can be also the fraction. Okay, fraction and number of times it occur over the total number of observation. So this, when we do this, when we calculate it as a fraction, so it becomes the same as probability. Okay, so it can be here, y-axis can be number of occurrence, and it can be the fraction, okay, of the occurrence, which is the probability. So this sums up this figure for A. This is the time series. Each year you have a data, so it looks like this. This is an example of a precipitation, annual precipitation. So each year you have the data. So for A, this is time series. Okay, and for B, this is histogram. Okay, so it looks into the number of occurrence or frequency. Frequency and number of occurrence is the same. So here it puts y-axis here as number of data. Okay, so it doesn't matter which is y or x, but if it measures the number of the frequency or number of occurrence, or in this case it put as number of data, so it becomes histogram. Okay, so before you know it as probability, histogram. Okay, so histogram is actually the same as probability. It can be the same as probability, but it is discrete. Okay, discrete means the data is in the range of some values. Okay, so it is discrete. But here you also have probability density function. So if you see here, the y-axis is probability and the x-axis is the data, annual maximum flow. So for probability, you cannot see like a bar chart, right? It's a continuous line. What I mean this by continuous line is you can see this line is continuous. Okay, so this is because probability density function is a continuous form of probability mass function. Before histogram, if it is the y, if it is measured according to the occurrence over the total observation, so you have the probability also, but it is for a discrete form. Okay, but for continuous data like this, it is called probability density function. So this is, we can relate to this is as a population. Okay, this is like a population. For histogram, it is a more suitable for a sample. Okay, you have a sample. But for probability density function or PDF, it represents a population. So this is also we can call this as a PDF. Okay, so it should look like this. Okay, y-axis is probability, but here it uses f, z, but it's the same. It is also probability, and the x-axis can be a data. Okay, it can be any data. Okay, so PDF actually can show you many things according to the data probability distribution. Okay, so how do we relate it with descriptive statistics? For example, here, if we have this kind of shape, for A, this is standard deviation, the difference between the shape against different standard deviation. So here, okay, remember this y-axis is probability P and x-axis is x, any data. So it shows you the if you have a small standard deviation, it means the range here from the minimum and maximum value of x is smaller compared to larger standard deviation. Okay, the minimum and maximum of the x or the data is larger, so that is what we call standard deviation. And for here is skewness. Skewness means either it is skewed to the right, positively skewed, or skewed to the left, okay, negatively skewed. So this means, for example, this one is negatively skewed. So negative means it's there are a lot of data on the left tail. Okay, there are more data on the not more data. I mean the range of. Wait. Okay, you can see here the range of data. Okay, for x is a lot on the negative side. On the left against the center, okay, on the left. So we have a lot of data here. Okay, compared to this area. Okay, so this is what we call negatively skewed. And for positively skewed, we can see here. Okay, let's say this is the highest probability point here. So we have a lot of more data on the right side. Okay, so this highest point, what is this highest point? So this is actually it is the highest probability. So the highest probability here, we can say this as the mean. Yeah? Usually the highest probability is the mean, the average. The mean, not average, is the mean. MEAN, not MIN, mean average. So okay, for example, this one is positively skewed. It means that there are a lot of data, okay, on the right side compared to the, like this one, compared to the left side. Okay, you can see here a lot of data on the right side. So this actually describe the kind of distribution that we have. For example, in Kelantan, we might have more data, okay, on the right, because we have more data which have high values compared to data on the left, which is lower than the mean or average values. So okay, it's okay if you don't understand yet, but this actually shows the kind of distribution of data that we have. So we have PDF, probability density function, and we also have CDF, cumulative distribution function. So cumulative distribution function is just the cumulative of the PDF. It's just the accumulation of the PDF. So in the end, you will get this kind of graph like this. Okay. So the total, the highest is 1, because probability, if you total all, you should get 1. Okay. So the highest would be 1. Okay. Before the highest is the can be the mean or the average. It can be that, but sometimes it's not. But for CDF, just you should understand the highest is 1, because in probability you can only get until 1. Okay? So as a summary, sample and population. Okay, so sample, we can also say it is discrete, DISCREET, discrete. Population is continuous, continuous. Okay, so both looks into the probability. Okay, so for sample, it is we use histogram. Okay, relative frequency function. It can be called a lot of name. It's okay if you get confused, but this is similar to histogram. Okay, this one is similar to histogram. Okay, and here is PDF. Okay, so this is PDF, probability density function. And that is the difference between sample and population. Okay, for sample, in terms of the frequency, number of occurrence, we use histogram. For population, we use the PDF, probability density function. So the difference also is, for sample, it is discrete. For example, like this bar chart, it is in a range of values. Okay, but for a population, it is a continuous line. Okay. And what else is okay, if you cumulate a cumulative of the histogram or the cumulative of the PDF, so you will get this under these two under graph, B and C. So if you accumulate the histogram, you will get this kind of graph. Okay. But if you accumulate a population or a probability density function graph, you will get this kind of continuous line. Okay? So both will have the maximum value of 1. Okay? So this is the basic of probability analysis actually. So I hope you understand this. Okay, so this is more explanation, but for your syllabus, I think I will not teach this in detail. This is more advanced on probability, so I will skip this. Okay, here is also some comparison between the histogram, and so A is relative frequency function, or we can also say it as histogram, and B is the cumulative frequency function. So this is actually, it compares sample and fitted. So fitted is usually the population, okay? But here it make it looks in like a discrete form. Okay, it's not like a continuous line for A. But for B is we can see that you can compare. Yeah, you can actually combine discrete and or sample and the population. For example, here we have a normal distribution population. Okay, so the continuous line is shown here as fitted, and the dots are samples. Okay, so enough on introduction. Okay, but the concept is that in probability you have samples. So you use your sample data to predict or to form some kind of a population model. So that is what we do in probability or frequency analysis. So here are some examples. So are you familiar with this figure? Okay, so this is a return period or IDF curve. It relates the duration, storm duration against rainfall intensity and the return period. So this is used for design. Okay, so you are graduating as a civil engineering, so a civil engineer. So to design this is how we get the design rainfall. So it has this return period or ARI, okay, average recurrence interval. So it's the same as return period. So it is the same. So how do you get these values? Because of frequency analysis. So this is how we get these points according to the values according to what return period. So it is taken from frequency analysis. So again, here we show some time series. Okay, if you plot the time series, so these are stations from Kyoto, Osaka, Hikone in Japan. So all of these are rainfall data. Okay, annual maximum, daily rainfall data. Okay, and then it can be represented in terms of probability. So here you see, for example, we are looking into Kyoto rainfall station. So you can see here, you can superimpose everything. Yeah? For example, the histogram, which is from the sample. And then, okay, all these lines, all of these are population, okay, represented by distribution models. So we have a lot of distribution models. So what we usually do is we need to fit which distribution models is most suitable for your sample data. So this distribution models comes from population. Okay, so we predict the population distribution. So how it is, we can predict it, and we can test. There's a lot of distribution models, so we can test which one fits our histogram or our sample data. So this is what frequency analysis do actually. Okay, so from the histogram, we fit according to which distribution model fits best. Then we can do the PDF, probability density function. Okay, so from PDF, we can get the CDF, cumulative distribution function. And from here, okay, so from here, we can get the ARI, okay, the return period. So us as engineer, so what we need is actually the return period or the ARI, because we want to design the rainfall. So if we want to design rainfall, we should estimate what is the return period values according to what design year you want to do. So this relates everything from PDF to CDF, okay, and then to return period. So this is basically the concept, okay, how you get your return period values. So fx is actually probability values. Okay, x is the data. Okay, so fx it is actually not as simple as this. It is some kind of formula. Fx equals to some kind of formula. Okay, so there's a formula here. So from that you get the CDF, and then you can get the return period. Okay, so before it's all about example of the population, okay, population models. But for your syllabus, you need to understand how to calculate using sample data or discrete, okay, discrete method, okay, which we call it as plotting position. So for your syllabus, for calculation, you use this discrete method or plotting position. So again, frequency analysis, you may use discrete data or continuous distribution. So discrete data use the plotting position method. Okay. For continuous distribution or the population, you use frequency distribution models, okay, as shown in part 1. Okay, so for probability plotting, there are also a lot of formulas. Okay, so basically, okay, so TR is recurrence interval, is the same as ARI. So the variable that you need to know is N and M. Okay, N and M. So M is event ranking. So you rank your rainfall data from largest to lowest. So 1 is largest and lowest is the number of data you have. I will show you later. Okay, and okay, this means events can be annual maximum series, maximum mean daily flows, or others. So this might be from a rainfall period of 1 day, 2 day. Okay, this is quite similar with the space a sample space we have mentioned before. So this events means the data that we rank. It can be annual maximum, it can be any data. So an example here, we have the maximum mean daily flows for water years. The data is from 1882 until 1967. Okay, saja je nak bagi data lama. Okay, so we can rank this from highest to lowest. So here in this table, you see the date, and then you see the not the year, and then you see the maximum Q value, and not this is maximum mean daily flows, so maximum mean daily flows, and you see the rank. I'm talking here the year, the data, okay, and the rank. So rank is you organize, you rearrange from highest to lowest, so that is rank. And then you can calculate the return period. So for example, here uses the Weibull plotting formula. Okay, and then here it shows the percent probability. So here using a simple formula. So percent probability means 1 over the return period. Okay, so that is the percent probability, 1 over the return period. So you get the percent probability. So this is an example of data. Okay, so we have finished plotting position. So now frequency factors. Okay, beside plotting position, I forgot to mention, you are required to also learn on how to estimate the return period using frequency factors. So using frequency factors, actually you will use a normal and Gumbel distribution. So both normal and Gumbel are continuous distribution and kind of a population distribution model. So the simplest way is using frequency factors. So this is for frequency factor. Okay, once a distribution has been selected and its parameters estimated, and then we need, how do we use this? Okay, for example, we want to find the return period using a normal or a Gumbel. Okay, so there is a really simplified method where you use this formula. Okay, so xt equals to x bar XT, which is the estimated event magnitude, which is if you want it as a 10-year return period. So this is a 10-year rainfall. So XT is 10-year rainfall equals to the mean, okay, the average, the sample mean, plus KT. KT is the frequency factor, and S, okay, S is the sample standard deviation. Okay, so for this frequency factor method, the frequency factor here, KT, so this will differentiate the value of KT, differentiate whether it's normal or Gumbel distribution. So for normal and Gumbel, it has its own KT value. Okay, but X bar, the sample mean, and the sample standard deviation would be the same, okay, because it's from the sample. So what's the difference is the KT. Okay, so for normal, KT is different, and for Gumbel, the KT is different. Okay, so remember I showed you Fx. Okay, this Fx is the probability. You can see back at the previous slides, Fx. You can ignore this big X. So Fx is the probability formula. So for normal, this is the formula. Okay, you don't need to remember this. What you need to remember or understand is this KT. Okay, but for your case, for calculation, you will just use this table. Okay, for estimating KT, you use this table. So in exam, it will be given. This table will be given. So depend on what return period you want. For example, here you want a 50-year return period rainfall value. So you need to look at a 50-year T. T is return period. So 50-year T. The probability is 0.02, and the KT value is this. Okay. So this is KT value. So what you need to do is just put in the value here. Okay, just put in this. Okay, so this and this is the same. KT and ZT is the same. So once you have the mean sample, X bar is the sample mean, and you have the sample standard deviation S. So just you put KT, and then you will get XT. Okay, so the other one is Gumbel. Okay, so for Gumbel, I repeat, if you want to find some return period value, so you can either use normal or Gumbel. So for Gumbel, the difference is it's KT. Okay, so for Gumbel, this is the formula for KT. Okay, so that's the difference. The general equation is the same. Okay, but the difference is in KT. So for normal distribution, KT is different. For Gumbel, the KT is different. So you will have an assignment and you need to do this. Okay, this is important. So here we have some example just to show you how to calculate. So for example, it gives an annual maximum rainfall series having its mean as, okay, so we have its mean value and we have its standard deviation value. And then you need to calculate a 5-year storm, okay, using frequency factor, okay, and Gumbel distribution. So for Gumbel, this is the formula, okay. For Gumbel, KT, this is the formula. So what you have to do is put KT in this general formula. So you have X bar, so X bar is the mean, you have X bar, and you have S, okay, S is the standard deviation given. So what you need to do is just put in the value, the return period 5 years. So put 5 here. Okay, so this is 5 here. So see, you have 5 and 5, and you get KT value. So then you can calculate the rainfall, okay, for 5-year return period here. Okay, so this is a really short example. So use Excel again. So that you can easily change the values. So determine Q for this 1, 2, 3, and 4 return period. Okay, this is return period using normal and Gumbel. So use Excel. Okay, you need to find the mean. You need to find the mean and standard deviation from these samples. Okay, so you can use Excel formula. Use Excel. You can just Google how to calculate mean and standard deviation using Excel. And then just use the formula and get the Q for 10, 50, 100 and 200 year return period. So this would be your assignment for chapter 9.